I'm Sebhat from Fluxim, and in this tutorial I would like to demonstrate the simulation of curved display backlight units with Fluxim's 3D ray tracing tool Laoss Optics. Let's start with a brief introduction to the problem of light management in curved optical elements. Today, there is a wide range of applications based on non-flat optical structures, from LED car lights to flexible luminaires and curved OLED displays. All of these applications require dedicated features for control of light guiding and outcoupling due to the curved geometry. However, most microtextures for beam shaping are designed for flat devices, and their appropriateness for curved geometries needs to be evaluated. Here, we consider, by means of optical simulation, the impact of curved geometries on beam shaping and control of light outcoupling via microtextures in backlight units for OLED displays. In the OLED technology, the brightness is provided by a backlight unit that illuminates the OLED stack from the rear side. Here we consider the common case of an edge-lit backlight unit, where the light from an LED is coupled into the backlight from the side and exits towards the OLED stack at the top. In addition to the light guide plate with the side-emitting LED, a standard OLED backlight unit contains a bottom reflector sheet, a diffusion film, as well as one or several brightness enhancement films. The light guide plate itself enables the directed propagation of the light via total internal reflection. However, to couple out the light uniformly, some bottom roughness features are required, whose density increases with the distance from the LED to compensate for the decreasing amount of light left in the light guide. The beams are then widened and redirected by the actions of diffuser and brightness enhancement elements. The main challenge in the design of a standard flat backlight unit is to achieve uniform outcoupling at the top surface in terms of both spatial intensity distribution and angular characteristics in spite of the edge illumination. In the case of a strongly curved backlight unit, on the other hand, the internal angular distribution of the light in the light guide as well as the directional characteristics of the light outcoupling are drastically altered. In addition to the uniformity of the spatial intensity distribution and of the angular characteristics, there is therefore also the aspect of directionality of the light outcoupling to be considered as a simulation target. In the following, we will show how to perform simulations of curved backlight units using the 3D ray tracing tool Laoss Optics that constitutes the optics module of the large area optoelectronic simulation software Laoss. Laoss Optics describes the propagation of light through optical media in the regime of ray optics via the use of a 3D ray tracing algorithm. The rays are generated at the source with random angles and intensity according to the angular spectrum of the light source. The rays interact with optical components via refraction and scattering, and the intensity is attenuated according to the extinction coefficient and distance traveled in absorbing media. Rays are then detected with spatial and angular resolution. For ease of both implementation and model parameterization by the user, Laoss Optics follows the lasagna approach for the definition of the device layout. This consists in resolving the structure by individual layers and the corresponding interfaces. The layers are characterized by thickness and composition in terms of optical data, that is, refractive index and extinction coefficient. The interfaces, on the other hand, are characterized by their geometry, which contains 2D domains with passive and active optical properties, and their 3D topography described by an XYZ file or a triangulated surface. Let's now see how this looks like in practice. Here you can see the graphical user interface of Laoss Optics with the definition of the backlight unit layer stack from the bottom surrounding to the top detector. Here the names, thicknesses, and optical data of the individual layers can be set. The interfaces then have to be parameterized using the interface dialog, where geometry and topography data can be loaded. Before proceeding with this, I briefly show how I generate this input for the flex-enabled backlight unit using a Python script. The script contains routines for the generation of the topography files of the encasing, bottom roughness features, spacer topography, and the brightness enhancement prism films, as well as geometry files for the encasing interface and different cover elements to conceal the LED hotspot. It defines the geometries of all the elements with a consistent set of parameters shared by the input generation routines. For instance, It determines the dome-like shape of the bottom roughness features, their initial and final spacing, as well as the speed by which their order increases. Let's now go back to Laoss and start with the parameterization of the first interface, which describes the encasing of the backlight, including the LED, the bottom mirror, and part of the enclosing frame. First, we import the topography via the import dialog. The different import formats are XYZ file, triangulated surface data, as well as generic 3D data as exported from common CD software, for instance in the form of an STL file. In this way, arbitrary surface topographies can be considered. However, for the flat backlight unit, the topography can be represented by a simple XYZ file. We now proceed with the parameterization of the different domains of the interface geometry: the bottom mirror, the LED in the left wall, the rest of the left wall, and the right wall. For the bottom mirror, the passive optical properties are specified via an angular transmission file that sets the reflectivity to 1 for all angles. For the LED, we select top emitting and import the corresponding angular spectrum. For the passive optical settings, we choose the diffuse reflective properties of white paint as encoded in a bidirectional scattering distribution function. This BSDF scatters light into a large range of outgoing angles and was obtained from an optical simulation with Fluxim's device simulation tool Setfos using a me-particle scattering algorithm. And such a Setfos BSDF simulation can also be performed directly within Laoss using the Laoss Setfos integration feature. The same BSDF is also used for the light scattering properties of the left and right walls. The 400 micrometer thick light guide plate is separated from the bottom reflector by an air gap whose size needs to be at least equal to the height of the bottom light out coupling structures. The interface between this air layer and the light guide plate layer implements the bottom roughness via its topography, and geometrical scattering is then enabled via the Fresnel interface condition. In Laoss, simple and regular scattering topographies can be generated easily via the topography import dialog. For instance, we can generate a regular 2D inverted micropyramid array on the whole area of the light guide plate using the topography generation and transformation options offered by the dialog. In this way we can generate large-scale textures in a matter of seconds. For the purpose of the backlight unit, however, we need a more complex arrangement of flat and hemispherical domes in the XYZ file generated by the Python script. This spacer topography for optical decoupling of the light guide and the diffuser is implemented in the form of prisms with semi-ellipsoidal profile oriented along the light guide plate length. Again, the thickness of the following air gap needs to be at least as large as the height of the spacer topography in order to avoid intersection of interfaces. The diffuser is implemented as a 100 micrometer PT sheet with a planar top surface that scatters incident rays into a cone of 20 degrees opening angle. This scattering behavior is implemented via an azimuthal BSDF file. The planar bottom interface, on the other hand, contains a geometry with two LED concealing cover regions as present in the benchmark backlight. The area right on top of the LED is covered with a diffusively scattering white paint implemented via the Me BSDF, and the one to the right of it features a perfectly absorbing black material described by an angular RT file with zero transmission and reflection. After another 100 nanometer air gap, the stack is completed by the brightness enhancement film, which is implemented in the form of a 50 micrometer polymer film with a triangular prism topography generated via an XYZ file import. The top interface also features a geometry that includes again a black cover domain. Finally, the Show Stack option can be used for visual inspection of the complete device stack. We now consider a backlight unit with semi-cylindrical curvature. Geometry and topography files are again generated via a dedicated Python script. A curved geometry requires a slightly different approach to the setup of the layer stack. While the sequence of the layers and interfaces is still the same, most of the layers need to be defined with vanishing nominal thickness. As for a cylindrical curvature, the thickness is now along the radial dimension, meaning the position of the layer surfaces is given by the radii of curvature of the interfaces. In fact, any interface, including the formerly plain or smooth ones, need to be defined with the appropriate curvature, which in some cases can still be achieved via an XYZ topography. More complex topographies like the bottom roughness or the brightness enhancement prism film, however, can no longer be represented unambiguously in this way, but need to be provided as a 3D surface. That is, not only the XYZ coordinates of the individual points need to be given, but also the triangles that linearize the curved surface. Since the geometry definition results from the projection of 3D faces onto 2D domains in XY plane, the geometry files have to be modified as well. As an example, we show the topography of the encasing, which is imported as a 3D surface via subsequent loading of the point and the triangle files. The geometry contains the same domains as in the flat case, that is, the bottom mirror, the LED, the left wall, and the right walls. However, the formerly perpendicular wall domains now extend into the XY plane. Since generating the triangles by hand is very cumbersome for topographies with large complexity, such as the dome pattern, Laoss offers a bending transformation in the topography import dialog, which can be used to bring the flat dome topography generated by the Python script into the required curved shape. Here we see the flat topography as loaded via the XYZ file import. We now choose the bend operation from transformations. The bending axis is along X, and the radius of curvature corresponds to the length of the light guide plate divided by pi. Since bending is with respect to the center of the structure, the curved surface needs to be shifted back laterally in order to correctly place the light guide plate bottom surface. The shift is performed using the transformation option translation, and the size of the shift can be inferred from the minimum extent in X given in the file properties. After the import of the surface topography, one should check that there are no intersection of interfaces, as the vertical separation is just 1 nanometer, and the two curved interfaces, encasing and light guide bottom, coincide under visual inspection. The correctness can be verified by selecting the respective default geometry domains, which are then highlighted in red. The entire lower surface should be highlighted when selecting the encasing interface, while the upper face of the curved structure should be defined completely by the dome topography interface. Similar procedures have to be performed for the surface spacer topography and the brightness enhancement prism films. After finishing the definition of the model layer stack, the simulation settings have to be specified. Individual simulations are performed at a single wavelength, but sweeps over a wavelength range can be performed in the case where spectral information is relevant. Requirements on resolution and number of rays depend primarily on the kind and accuracy of the information that the simulation should provide. For instance, high spatial resolution for the assessment of uniformity and sufficient angular resolution for the investigation of angular light outcoupling characteristics. The maximum number of hits per ray should be large enough, such as to avoid rays to be killed prior to outcoupling. The setting border type is used to impose periodic boundary conditions in the lateral dimensions, which is appropriate here in the case of a reduced model size with only one LED. We can now run the simulation. Depending on the complexity of the model and the simulation settings, simulations take from a few seconds to many hours. Simulation time can be reduced by running on multi-core workstations, as Laoss fully exploits multi-threading. Once the simulation is finished, the results are post-processed and represented in a number of relevant quantities. There are two basic levels on which the simulation results can be assessed: a qualitative level, which permits fast verification of target functionality, and a quantitative or photometric level on which optical performance can be measured. A very intuitive and visual post-processing tool are the sample rays. The 3D rendering of the detected rays demonstrates both the guiding and outcoupling of the rays over the whole length of the light guide plate and the angular uniformity of light extraction. The functionality of the different component layers can be verified by a close-up inspection of the ray behavior. Spatial uniformity can be quantified based on the XY intensity plot. There, a cross-sectional cut provides the evolution of light outcoupling with distance from the LED. Angular characteristics of light outcoupling can be inferred directly from the polar plot. If a spectral sweep was performed, additional information on far-field color appearance and luminance is available in both spatial and angular resolution. Finally, spatial and angular characteristics can be propagated away from the physical detector by using the movable detector feature. The remote detector can be of reduced size and also tilted with respect to the physical detector. As an example, we define a 5 by 5 mm detector placed at 5 cm from the top surface and tilted by 30 degrees. Due to its size and position, the remote detector will require a very large number and resolution of initial rays to provide accurate data. This concludes my hands-on presentation on the modeling of curved display backlight units using Laoss. For further information, please visit our website at www.fluxim.com/Laoss. Thanks for watching.